Okay, so we've got this circle with radius 2. And that's C. And so they're talking about this vector field 4x plus 2y. Let's do this in just a second. What is the vector field? 4x plus 2y, x squared plus y squared equals 4. So 4x. So this is what we're talking about here. Here's 4x plus 2y. And so this is kind of like, imagine, a two-dimensional flow field. And then so we can talk about, we haven't before, but we can talk about flux out through the boundary, like through the thing. So through C, right? So that what is the flux out of that? So it's kind of, so we don't want to do f dot dr, because what does f dot dr do? What is that? What happens with that? So we accumulate all the forces dot dr. What's that? What does it mean to accumulate dot dr? So if we parameterize this surface as some function, or this curve as some function r, then values of that vector function, say this is say r1, okay? R of say x1, y1. What is dr? What's dr represent? The derivative of a vector function is what that gives a new vector function that tells us what? What's that? The normal? How quickly we forget. What does the derivative of a vector function that gives us a space curve, right? What is the derivative of that function? Is a new tangent. Yeah, so that dr is going to be these vectors that are tangent to, right? So the magnitude is kind of the rate at which the curve is swept out with respect to t. Remember this? Because this is like r is a function of t. So, sorry. So r is a function of t, right? R is a function of t. So then the magnitude of that is the rate at which the curve is being swept out at the given value of t, and the direction is the direction the curve is being swept out. So if I do f dot dr, is that going to be flux? What is f dot dr going to be? So I'm looking at, say, what's the vector f at this point? It's something like this. So what does f dot dr achieve? No, it could be anything, right? So it doesn't, I'm not asking for an answer like that. So suppose f is like this. Okay, what does f, it's not, but what does f dot dr achieve? What does that do?
The value of the vector field as much as the direction of the tangent.
Yeah, it's going to give me the component of f in the direction of dr, right? It's going to give me the component of f in the direction of dr. F dot dr is going to give me something like that, right? And so then I'm going to accumulate these all the way around C. Is that going to be the flux out of that curve? No, that's going to be like the work, right? That's like the work integral. So taking all those force vectors and accumulating them in as much as they're in the direction of the curve. So what would flux be then? What would flux be? If that's kind of like work. If F is a force field, then that's like the work that the force field does as the particle moves around that curve, because it's in the direction of motion, right? F dot dr. So flux we could write how? Like what? F. Well, what do we want with flux now? We want F in as much as it is, yeah, orthogonal to, right? Orthogonal. So we want F in as much as it's orthogonal to the curve, because we want how much flow are we getting through the curve. Now, the problem with, so this is the idea, right? This is the idea of this. Now, this gives us something in R3, because the cross product is going to be, but I'm just kind of showing you that this would be like the work, right? So that taking all the amount of force in the direction, F dot dr versus F cross dr. So this is kind of what the idea of this is. F dot n ds is taking the dot product with the normal to the curve, which gives us the components of F normal to the curve, ds. And so that's like the flux out of this. Okay, so then what would it, so then as an analogy to the divergence theorem, what would that equal? So the flux out the curve would equal what? We've learned anything in the lectures of recent. So the flux out of the curve would be equal to, what's that? Right, so it would be like summing up all the little flux out of little elements in the middle. Remember, that's what the divergence was. So if we broke this up into a bunch of little elements inside, and we summed up the flux across the area, that whole region, and summed up all the flux out of the little, right? So this is kind of a 2D version of the divergence theorem. That we could partition up the region, and we could accumulate all the divergence out of all the little elements, right? And that would be the divergence out of each element times the area of that element would give us what? The flux out of each flux out of it. So this is like the flux out of a typical element. Okay, that's good. That's not cheap. So and this is kind of the pattern we've seen kind of over and over with the divergence theorem and Stokes theorem. If we cut this thing up into little elements, and so we took one little element, we can calculate the flux out of that by the rate of change of flux divergence times the area of that little element. And if we sum all those up, it'll be the same as the flux coming out of just the boundary. Why? Because all the shared size cancel out. Remember that? So this is the easier way to solve this. All right, so this is like a two-dimensional version of the divergence theorem. There's also a two-dimensional version of Stokes theorem. Who knows what that is? So what is Stokes theorem? Stokes theorem says that the double integral of f dot ds, or curl. We'll talk about that Friday. Let's just talk about that Friday. All right, so are we good on this example here? Okay, but so those questions I was asking you about, like what does this give, and what does this mean? Where does these theorems come from? These are important. These are important questions. So you got to go back and watch the videos. Just knowing how to do the Weber problems is not enough. You have to understand stuff that we talked about in class. All right. So there's so many things to talk about and so many problems. So that's why I encourage you guys to get with me in office hours, find me, make appointments. I'm not going to talk about this one for time's sake, but there's so many like rich conversations to have around so many of these problems. What's this one? Oh, this one's the one that was due today. So this one was the M is a cap cylindrical surface, which is the union of two surfaces, a cylinder and the hemisphere cap. So we have to first conceive that surface. So there's a cylinder and the cap. So we put it together like this, but then once they're together, then just imagine that seam doesn't matter anymore. Just take that seam out of there. And just imagine this is all one surface, right? This is all one surface. It's just the cylinder and then the hemisphere cap. So this is all one surface S now. And is it an open surface or a closed surface? Open or closed? Oh, you were better on the first try. This is an open surface. Why is it an open surface? The bottom is open, right? So this, it's not, and it doesn't have an inside and an outside. It has more like a top and a bottom. Okay, so imagine an ant on the surface crawling around. So if it's an open surface, that means the ant will stay on one side until the ant crosses the boundary, and then once it crosses the boundary, it's on the other side. So you can imagine that the top of this and the bottom of this, so where is the boundary? So the ant's crawling around here. Crawling around. So has it crossed over to the bottom side yet? How does it get to the bottom side? Where does it have to go? The circle at the bottom. Once it crosses that circle at the bottom, then it can get on the inside, where the bottom of it. So like for the cylinder, the outside of the cylinder is part of the top of the surface. Do you see that? And the inside of the cylinder is part of the bottom of the surface. Can you imagine that? So that's the key to this problem, that you have to see this silo. It's like a silo without a bottom, right? A silo holds grain. You see them on the highway if you're in the Midwest. And so it's this thing, and then the surface, and then it's open on the bottom so that so like the outside, what you could see if you were standing here is the top. If you were standing inside there on the ground where it's open, now what you could see would be the bottom. Does that make sense? So then if we're going to use Stokes Theorem to get this flux integral, we're really going to then what? We're going to do the line integral around, this is the boundary, so all we need to do is the line integral around that boundary. So this equals then that single C, the circulation of F. So we're going to use this F. We're going to parameterize that circle in the XY plane, and then use that parameterization to rewrite F, and then do this. Okay, so this was a challenging problem, low success, so does that help? Is that better? Yes, please.
Which way would you orient the curve?
Okay, so I would assume if they don't say anything, then like upward orientation is positive. So if upward orientation is positive, then which way would C go, right? So that would mean upward orientation would mean that once you get down towards C, it would be like outward on the cylinder. It would be the same as upward. You see that? So then remember what you do? You go around like this. Like, so if that's positive by the right-hand rule, you look at the direction according to the right-hand rule, and when it gets close to that C down there, that's the direction of C. Remember that? So, I don't know, did that make sense? So here's the bottom. So take an N, so that's the upward orientation of the surface, and then according to that, it would be counterclockwise like that. So that means you look at where it's close to C, it's going to go the same direction. So C would be oriented this way. Does that answer it? Cool. All right, other questions on this? So that's how you're going to solve this. You probably do not want to take the curl of this and try to do this this awful surface, which would be the union of this sphere, which we know are not fun, and it's a sphere that's up in the air, right? It's not centered at the origin, so that makes it even worse. And then the cylinder, so you definitely want to do the line integral around the boundary between the top and the bottom. Okay, yes please.
I have a question I wanted to ask earlier about the homework, but could I ask that?
Maybe.
It has to do with everything, not just...
Okay, sure.
So for the divergence of f, it was 2x plus 1, and so you could just do the triple integral dx r dr d theta, cylindrical coordinates. But what if it was like 2x plus y? Then what would you do? Would you make y r cosine theta and then do it?
Well, however you're parameterizing the solid. Wait. No, so because dv's, so I mean, if you're in rectangular coordinates, you're going to have dv is going to be. So you're saying it's going to be then in like cylindrical coordinates, your dv?
That's what, because it was a half cylinder, so I just put the volume as cylindrical coordinates. But if it had a y and a divergence, would you change the y to be matched it, or would you have to use rectangular coordinates?
I need to see the problem, but that's okay. But so basically, you have to be able to write x and y in terms of the whatever three variables you're using for your dv. So if you've got, like you're saying, you got x and then dr, x, r dr. What is that? So dx, r dx dr d theta, something like that. And you're saying, what do I do with y? Well, y has to be, y is a function of r and theta then.
Okay.
Right, so you have to rewrite y in terms of r and theta.
Okay.
Yeah.
Would you do that right when you took the divergence of f, or would you do it after you took the divergence of f? Because it's dx.
The only divergence formula we have is when we have x, y, and z, right?
Okay.
So do the divergence and then change it into cylindrical coordinates in the triple integral. Yeah, so y is going to be in terms of r and theta. Okay. Other questions? So, like I said, there's so many, on these homework problems, there's so many conversations to be had. I encourage you to find me, make an appointment. Let's have these conversations. Here's a good example. Let's talk about. So what's nice here is, and this is kind of a first, is we've got through all the material of the course, and now we have a day and a half to talk about some, just keep talking about it, and do practice, but then look at some interesting situations here. So here's the situation. So I have a vector field F that I'm showing you, and then I have this surface. Is this an open surface or a closed surface? It's an open surface, right? So that means it has two sides. So it's orientable. It has two sides, which are separated by a boundary, right? So I want to first of all predict whether the curl of the vector field F shown is positive, negative, or zero. So I'll show you that the z component of the vector field is 0. Let's give a good view of this here. That's a pretty good view. So what do you think? Do you think that the curl is positive, negative, or 0 of this vector field? This is looking down, right? This is looking down. All the z components of F are 0. What do you think? Positive, negative, or 0? Looks positive. Positive?
Not positive.
He's not positive, but he thinks it's positive. Lauren didn't like that. Comments? Are we all in agreement that it's positive? The curl is positive? Yeah.
I think it's negative.
You think why?
Because like if you imagine like putting a flywheel at some point, I sort of see it being turned like clockwise. Because like the vectors closer to the origin have like a bit larger magnitude, like further away.
Okay, so because the vectors closer to the origin are larger and they're getting smaller as you go out, if we put a flywheel in this thing, that ones that are close to the origin might make actually the flywheel turn this way, even though the holes globally it's turning counterclockwise. What do you think? So what do you think? Is it positive, negative, or zero? Does everyone understand that point? Curl is not a global phenomenon of a vector field. It's a local phenomenon. So yes, a flywheel will travel in a big counterclockwise circle, but how is it spinning locally? That's the key. So does the silence mean you don't know?
So is the curl just negative everywhere and positive at the center?
No. So you're saying that you think the flywheel is going to turn clockwise? Is that what you're saying? Everywhere? You're saying it's positive?
I guess.
Don't know. All right. Well, let me show you the vector field. Here's the vector field. There's the x and y components, and then the z component is 0. Anybody remember this one? What's the curl? It's not negative. It's 0. So you do this for written homework. So you found the curl of this, and you have to do the quotient rule. And the curl is 0. Okay, so in this particular case, the flywheel, yeah, it moves around in a big counterclockwise circle, but it doesn't rotate. It doesn't rotate. Okay? So just by looking at it, the answer here is you can't tell. You can't tell if, so it looks like maybe, yeah, these vectors are bigger towards the, I mean, that was the key thing to notice. The vectors are bigger, more towards the origin, and smaller as you get away. So that would give the tendency for clockwise rotation, even though the whole thing is going counterclockwise. But now that I show you, now you know for sure the curl is 0, because we've solved that one before. Okay? Next question. So if the yellow surface has positive orientation, is outward, the positive orientation is outward for the yellow surface, I want you to determine the positive orientation of the boundary C. So what would positive orientation of the boundary C be? And I want you to work on that and discuss it while I take attendance. Well, that's the right question. Good question of C. How about what is C? What's that?
Two separate circles, ovals, curves on the circle.
You're saying it's both. It's both. Is it both? It's both. It's both. So we need the boundary C is made up of both circles, both rings. Both rings together give us the boundary C. So we got to work them out separately. So what is positive orientation for this one up here? Look, is it this way? Is that positive? If our surface has outward orientation, is this positive? So how can you tell? You take outward orientation would be like that, and so then counterclockwise like this would mean you're going this way, near the surface. So, and what about the bottom? This way? So that's the orientation of C. C has two parts, and so each is, this one's oriented around this way, and this oriented around this way, okay? Find the flux through the yellow surface. Find the flux through the yellow surface. So I got to give you F, right? So, no, we know what F is. F is? Okay, that's our flux, or that's the flux field, or that's the vector field. We want to get the flux through the yellow surface. The flux through the yellow surface. So I'll tell you that the bottom ring here is that's x squared plus y squared equals 4. And the top ring is the ellipse, x squared over 9 plus y squared equals 1, z equals 5. Okay, and so then the yellow surface is what just show you. Is what joins those two, right? So it's like it's what joins those two from that x squared plus y squared equals 4 circle up to this ellipse x squared plus 9, x squared over 9 plus y squared equals 1. At z equals 5. So we want to find the flux through the yellow surface. Great question. I want to find the flux. Sorry, I want to find the flux of the curl. So what is so S is the yellow surface. So we're going to have to get an equation for the surface, right? No? No? Oh, what? What'd you say?
We had the curl solve for 0.
The curl is 0. So the flux of the curl through the surface? Phew, right? Okay, so next question is I want the circulation through the red path. So I want to get the circulation around the red path. So I want you to think about that for a second. How am I going to get the circulation around the red path?
Negative circulation of the blue path.
He wants the opposite of the circulation of the blue path. How come? Is that right? Ping Pei? Is that right? Should be? Why? What do you think, John C? How come? Okay, so like they would always be equal and opposite? Those two would always be equal and opposite? What's that? Only if the vector field is conservative? Well, and why? So why would it have to be conservative? What's the key here?
Because then whatever passes it through is any closed.
Stokes theorem.
What's that?
Stokes theorem.
What's Stokes theorem? Alex?
That the circulation around both of those curves is equal to the curl of the flux of the curl.
Right. Stokes theorem says that the flux of the curl equals the circulation around the boundary of F, right? And in this case, what is that? No, the circulation around F. In this case, how would we compute the circulation for the boundary of S? What would that entail? Yeah, so you're going to have two. You're going to have like a C1, like blue. Let's say blue. The bottom. plus top, right? C2. So this curl, the flux of the curl, is equal to, according to, by Stokes theorem, is equal to the circulation of the boundary. Well, that's broken up into two pieces, so we'd have to add them together. So if I'm asking you for this, what is the circulation of C2? So it's only equal and opposite to this because, yeah, the flux of the curl is 0. And the flux of the curl is 0 when F is conservative, right? It's irrotational, right? F is, so yeah, what you're saying is right. The F is irrotational, therefore the curl is 0. Therefore, by Stokes theorem, this has to be 0 too, right? The circulation around the boundary is 0, meaning that these are equal and opposite. So we can get this one by doing what? The opposite of? And that's easy. Right? It's just a circle in the xy plane. Easy to parameterize. And then you put F in terms of that, and you can find it. Okay, make sense? Yeah, please.
Is your vector field defined at the origin? Because that's where that curve goes. Did we do an example in class for the hole in the curve?
Right, but we're not but it's not a region that contains that hole, right? The surface is the vector field is defined everywhere for the surface, so it's okay. Right? The problem with that region, that vector field that was the region, is that the region was not simply connected. Right? This surface, this yellow surface, is perfectly fine because it avoids that. It avoids that singularity. Does that make sense? Because like all the points on that yellow surface are they're defined. Yeah.
Do we not know that if the vector field is conservative or not?
What's that?
Do we know if the vector field is conservative?
Yes, it is conservative because
both of them 0 still, like both curves.
no. So now when we do the curve, it won't be 0 because you have that singularity. If you're just thinking about just that circulation integral and you forget about the surface, it's going around a singularity, so it won't be 0. That's like the example we did.
Yeah. Oh yeah. That.
Right? Remember that? So yeah, so these will not, so yes, it would be, except for that there is that singularity on the z-axis.
Yeah.
So yes, these will not, yeah, and not equal to 0, that's right. So it is involved, that principle is involved when it comes to doing these line integrals. Okay, good questions. Any other questions? Okay, so I have another example here. All right, so find the circulation of F over C, where C is the triangular path in R3 from 301 to 120 to 002 and back to 301 if the F is this one, y squared z 3yx. Okay, so let's make a picture of that, and then let's talk about what this problem is like. So, 3, 0, 1, 2, 0, 0, 0, 2. So from 301 to 120. 002, back to 301. Okay, so we can call this like C1, C2, C3. And that those C1, C2, C3 makes up C, right? Makes up C. So let's talk about solving this problem. What do you think? So finding this circulation directly would mean what? What would that mean? 3 line integrals, right? So we'd parameterize that segment, we'd parameterize that segment, we'd parameterize that segment. For each one, write the vector field f in terms of our parameterization and do what? F dot dr, right? And then we'd sum them up, right? Which would be the sum as I equals 1 to 3 of Ci. C1 integral plus C2 line integral plus C3 line integral, right? Okay? The way to go? Is that the way to go? Fernando, why not? What are we going to do? You want to do something else?
I want to move it.
Oh, I thought you were shaking your head like that's not the way to go. I know Alex knows. Yeah.
You can use the
Stokes Theorem. Okay, so this same thing is equal to?
The double integral over the encloses the surface.
Okay.
Of the curl of ds.
Okay, is it so what surface are you thinking about for S? What is S?
That's the triangle. That's between all these lines.
Yeah, so we could think of a triangular surface for which our C is the boundary. And is that closed or open?
That's open.
Open, right? So that's an open surface, right? And that's what Stokes Theorem is for, open surfaces, right? With a boundary C. Okay, so we need the curl of F, and what else do we need?
Yes, you need to put like really normal to that plane.
Okay. So remember I suggested that if your plane is not perpendicular to one of the coordinate planes, you don't go the normal vector route. Yeah, so instead, what do we want to do? So what are we going to need to do this? We're gonna find that line integral, that circulation, by doing the flux of the curl. So and then we're going to, by Stokes Theorem, say that they're equal. So what do we need to do that flux? So we're going to find the curl, obviously. What else are we going to need to do that flux? What's that? So we want an equation for the surface, right? And when we get that equation for the surface, what will it be like? So what will be the most natural way to write the equation of that surface? As a plane, right? Z is a function of x and y. Okay, so we need to find the curl, and we need to find that function, the function for that plane. So I think the curl is, I'm just going to write down what the curl is. It is 3x minus 1. So I trust you guys can find that. 3x minus 1 minus 3y and minus 2y. Okay, so there's the curl. And so now we need to get the equation of that plane. It's going to take us back to, what, week 3 of the class. Can you get the equation of that plane?
Yeah.
Go, or find out from somebody, and go. So for the cross product, did you get 2, 5, 6? And then for the equation of the plane, you put that in your equation of your plane, right? 2 times x minus, I use 0, 0, 2 is the easiest point. So you get the cross product, the normal vector, and I use 0.002, but it doesn't matter. Use any of the points, you're going to get the same equation. Negative 1/3 x minus 5, 6y plus 2. Someone get that? Questions on that? So how are we gonna, now we're gonna write the So does anybody remember how we can streamline this now? Do you remember that if our surface is written as a function of x and y, that we did that as a special case? Do you remember that? Simon, do you remember that? You remember doing it, but don't remember what it is. Remember that? So that was, so this, when z is a function of x and y, this thing equals double integral over d, which will be projected in the xy plane of minus p partial respect times partial respect to x minus q times partial respect to y plus r. Is that familiar? dA. So we can avoid, when you have the function z as a function of x and y, you can avoid parameterizing the surface in two variables and taking the cross product and doing all that, and just go right to this, because we did that, we already did that for the general case when z was a function of x and y. And that's what we got. So we're ready to write it down. So double integral of, so now here's the key, our p, q, and r. What are our p, q, and r for this flux integral? The curl vector field, not the original vector field. The p, q, and r, because this is the flux of the curl. So you need the p, q, and r of the curl, not the p, q, and r of the original function. The original vector field. Does that make sense? So this p, q, and r is for the curl. Because Stokes Theorem, you're taking the flux not of f, but the flux of the curl. So it's going to be what? Negative 3x minus 1 times the partial of g with respect to x. Negative 1/3. Right? Minus q is negative 3y times the partial of g with respect to y. 5/6 plus r, which is negative 2y. Watch your signs, lots of negatives. dA. And so then what is d? What is d? What are we integrating this over? What's that? The projection of this triangle into the xy plane. Because this is going to be, so what will that projection be? It'll be this. This is the point, going to be 1, 2. So all you have to do is just truncate off the z components. Right? Just take the z components off, and you have the xy vertices of the triangle. 0, 0, 3, 0, 1, 2. Projecting that triangle into the xy plane just means removing the z components, just letting it fall right onto the xy plane. You just make the z components 0, take them away. So how are we going to do this double integral? What do we want to do? Type 2, right? We want to go this way first, and then we want to stack them up this way. So this is y equals 2x. This is y equals 3 minus x. But we're doing type 2, so we're doing x left to right first, which means x on the right to x on the left. So what is that? X on the right is, x on the left is y over 2. X on the right is 3 minus y of that dx dy. And that's from, y goes from then? 0 to 2. And you can check it later. It's going to be, you're going to get negative 6. Meaning that the flow is which way? So this loop, is that upward orientation of the surface or downward orientation? Going around this way. It can be upward, and so if you get negative 6, then you know the flow is down. Okay, please, before Friday. So there's going to be homework, check Blackboard homework, but look in exam prep, look at the outline. Everyone, you've got to start reading that outline. It's long, okay? It's 2 pages. So take a look at that before Friday and start studying. And there's practice problems too. And there's homework. Time to hit the books.